All right. Welcome back, or welcome to all of those who first tuning in for the second part of the Back to the Basics track, C++ templates. I'm Andreas Fertig. I work as a trainer and a consultant for C++. For all of those who were in the first part already know that. Okay, now I'm confused. Are we live or aren't we live? Okay, so we are live. Thanks. Okay, so let's do this one more. So welcome to the second part of the Back to the Basics track, C++ templates. My name is Andreas Fertig. I work as a trainer and consultant for C++. I told you in the first part for all of those who weren't there that I think it's quite nice and very great that we can have this event here despite all what's going on in the world currently and the situation we are facing. And the sadness about having it that way is that you see even less the people who are running this show, who are contributing to it, not by standing in front of a camera or microphone, but behind the scenes, like the two volunteers creating this live stream for you today and managing the templates and all that stuff behind for me, Atul and Giorgio. And there are all the others around John who made all that possible to be here, even if here maybe your own home. So as I said in the first part, one good idea is create in the question and answers section, create a question saying, give a round of applause to all the stuff for all the things they are doing, making this thing happen. And simply everybody who likes to jump in, upvote that. That gives them a little bit of appreciation, because if you're simply applauding at home, well, you have either to live stream it or send them the recording. That would be a nice idea, maybe as well, but they cannot hear it initially. So let's give them a hand of applause, showing them our appreciation. In the first part, we talked about function templates and class templates. We looked a little bit about what instantiation means and how we can control the resulting code from it. So guidelines for efficiently using templates here. The key is that we have to watch out for different instantiations and for which parts we can move out of the template because they're shared commonality, which can be used all over the place, things like that. We also looked at another construct like constexprif, which yields to only one branch in your binary in the end because it's evaluated at compile time, and it works with types. So despite there was only a small section where I specifically addressed thinking in types, a lot of my slides in the first part referred to types because we talked about how to instantiate a template, and often that's done by a type. Sometimes it's by a so-called non-type template parameter, and it's number, most likely. We have also seen or heard about the different types of template parameters. So we have type template parameters, probably the most common ones. Non-type template parameters whenever we are passing in a constant, or template parameters, which we will see in this second part now, what we can do with them or when we need them. We learned that we have function templates, class templates, and variable templates. I slightly skipped alias templates at the beginning, but we also looked in alias templates. Now, there is another thing. Since C++ 11, we can do with templates, or the ability templates give us, and these are variadic templates. And here we have such a variadic template as an example and all its different components. So a variadic template starts, as every other template, of course, with the template keyword in the angle brackets. I'm sure you learned that in the first part. And a variadic template is created by having 3 dots after type name or class. It's the ellipsis operator. We know that from maybe functions like printf, so variadic functions or variadic macros. And whenever we say type name, we can also exchange that and say class. There are a few minor exceptions where we only can either use type name or class. But in the case here of this template head, we can use either type name or class. I usually use type name. So what I'm doing here is I'm creating a variadic template because I'm starting here on the template head with type name t, comma, and then type name ... ts. And that refers to a variadic template. More precisely, we are creating here a template parameter pack because it's a type name, so it's a type parameter we have here. We can also create non-type template parameter packs. But here we are looking at a type template parameter pack. We can give it a name. We can omit that name if you don't like to refer to it later, like with every other type name or template parameter. And here, then I have a min function. It returns auto. It's const expr because I can. And if you remember or were there in the first round of the talk, then I already had the min function there. It took two parameters, a and b, by const tref, the same as here. But this time we have a third parameter that function takes, and it's of type const tsref, followed by the three dots. So this is the third parameter, which is somewhat optional, and this is the variadic pack. So here I'm looking at a parameter pack. And now that I have this type ts, I can create this pack out of it and can give it a name, which in this case is the small written ts. Now I can combine a couple of features we saw in the first part. We looked at function templates and at const expref at the end. And here I'm using that const expref because that min function is supposed to work with an arbitrary number of arguments, but at least two. Because a pack can be empty. It's like a printf. You don't need to pass any other parameter than a format string to it, and that can contain the entire string. And here it's the same. If you're looking down before peeking into the template itself, in line number 19 and 20, there I'm using it. I have this min function called in a static assert because it's const expr, I can do that. And the first time I'm passing 3, 2, 3, 4, 5 to it, and I expect the result is 2 because 2 is the smallest value in that set. And then I can also use it with only 2 parameters as before. So this helps you if you have the case where you need to pass more than 2 values into a function and figure out which one is the smallest value and get that back. And our function template does it a way that it first, in line number 9, figures out which is the smallest value of a and b, which is a smaller one, a or b. And it saves that result in a variable m. So that's more or less like before, but before we immediately returned that result. Now we only store this result for a moment, and then we have a const expr if there. And that const expr if inside does use my parameter pack because there is a special kind of size of. It's the size of followed by 3 dots, and I'm passing ts to it. And that means that I'm querying at compile time for the size of this pack. And size of this pack in this context means number of arguments in that pack. So the number of arguments you passed to that function to min the one followed by the first 2. So in my example, it would be 3, 4, 5. These are the elements in this pack. And the size of operator returns me as a result 3. It's not the number of bytes these types or these values would occupy. It's solely the number of arguments in this pack. I can query that. And in the size of, I'm checking whether there are elements left in that pack. And if so, I go and call min recursively, passing in the result I calculated before in line number 9, m, and my parameter pack ts. But with the 3 dots, that means that pack gets expanded. In that context, in D, I'm expanding the pack. And if you're looking at the signature closely of that function, you can see that I'm essentially splitting up the first argument from the pack because that now gets passed to min as argument B. And I use that technique to, with each recursive call, split up one parameter and reduce the pack until its size is 0, and I have the final result. This is a technique that often happens in Fertig templates, especially before, or if you're using C++ 17 and 14, then you have to do this recursion because there's no way to index into a pack. So it's not like an array where you can say, please give me the element number 3 or something like this. You have to slightly or slowly split up the elements. And this is the typical technique to do this. Guarded by the const_if, it's slightly better because the solely C++11 version, const_if technically is C++17. In a sole C++11 version, you would have to provide a min function or an overload for min with 0 or only 2 arguments to catch the case when the pack gets empty. But const_if helps me here to avoid that. So that's the essential parts of a variadic template. And variadic templates are really powerful. What can I do with them? So here is another example, slightly more code. And you start, hopefully, to get the feeling how templates look like. You see a lot of template keywords in there and a lot of angle brackets. But that's not really an issue. You just know that you're a template and that you have to parse it in your mind a little bit differently. So what I'm having here are, from the top, 3 different functions called normalize. And their purpose is solely to take either a std string, a q string from the Qt library, or a plain char string as a pointer and convert it back in a std string. So in the case of a std string, there's nothing much to do. In case of Qt string, I have to call toStd string on that string because that's the way how you convert a Q string into a std string. And for a char array, I just call the constructor of a std string and return it because the normalize functions return currently auto. As in the first part, it's not optimized for efficiency here, so you could squeeze in a couple of R-value references and std moves and so on to make it more efficient, but I did go for an implementation that still fits on a slide. So in real code, you would probably write it a little bit differently to make it more efficient. But it does the job. It does a pretty good job. So then I have in B this, say, catch-all template. It's a function template. It takes a single class name, type name T. This time I use class T just to switch it a little. And it once again takes only a single parameter, const tref, and it converts that thing to a std string by calling toStd string. Because the idea is that the first 3 functions essentially covered every string combination, and now it's no longer a string. It may be a number or something arbitrary else, and hopefully toString has knowledge how to convert it to a std string. That's the key idea here. With all that normalized functions equipped, we can now start using it. And the usage here is at the bottom, I have a function template called strcut. Its purpose is to concatenate multiple strings. If you're really looking for such a version, I highly recommend the version of std_absale. They do way more and a lot better job than this short snippet here, but this short snippet does the job. What I'm doing is stringcut takes a const tref as its first argument, and after that, it's a variadic template, so it takes my const tsref ... args. So it takes an arbitrary number of arguments. And what it does is, internally in line number 19, it starts with creating a variable called ret of type std string. This is the one which will be returned later in line 23. And it calls normalize on the first argument on targ and initializes my return value string with that result. So essentially, that's the first step of converting everything that was passed in as first argument into a std string. And after that, I'm calling this dash strcut function, which would usually go into a namespace or something like this. But as you can see, there were no more lines left on this slide, so I haven't had a chance. So I named it underline strcut, and you can see this function in line number 9. What it's passed to in 21 is the return value we created, so that std string, and then the expanded pack that the initial strcut function took. As you can see that by the args ... in D. Now my more or less internal template strcut, it takes as a first argument a std string by reference, so it expects that. The outer version didn't, so you could pass everything as a first argument to that outer version, even an int, but to the internal version, that one expects to get a std string as its first argument, because essentially, as we can see in the body, it appends all the following arguments to it, and simply it doesn't have to return it because it got it by reference, so it simply adds to it, and the outer function later can return the concatenated string. The second argument my internal strcut function takes is once again a const tref targ, and after that my parameter pack. So that pattern follows along the lines. It's the same as the strcut function before, with the purpose to have the ability to split up one argument from the pack as we see it on the previous slide, as we saw it in the previous slide. So and what it does there in line number 11 is call normalize and append this value to our return value. So whatever was returned by normalize is a std string by now, and we can return it, we can add it to red. And then we see the const if as before. It checks other elements in this pack left. So is the size of this pack larger than 1 or larger than 0? Sorry. If so, then in C we can see that strcut now calls itself repeatedly. Splitting up one element from the pack each time as before. So this is a pattern we're using all over the place when it comes to Fertig templates, as long as we have C++ 14 or less. And we have a question. Can inheritance and templates be combined to call, say, member function foo from base to derived by explicitly calling derived foo using class template type rather than dynamic pointer? Let me process that once again. Okay, I think the answer is yes, but reach out to me later. I have to process it in more depth. So that's Fertig templates, and that's the 11 to 14 version. I squeezed in const if there, so technically we are already used C++ 17, but there is one additional thing with C++ 17, and that's fault expressions. And fault expressions make that recursion go away. We don't need it any longer. We have two different types of fault expressions. We have unary and binary fault expressions, and there are once more divided into a right and into a left fault. So we have a unary right and a unary left, and a binary right and a binary left fault. And as you can see on the slide here, the unary form always has to form pack, then an operation. An operation is like plus, minus, as we will see here, the comma operator as well, and then followed by the 3 dots. And all that in parentheses. The parentheses are crucial here, otherwise it's not a fault expression. And what that means is that you have a pack, then you apply an operation to here, then the 3 dots imply that this thing gets expanded. So you can work on a fold, and this fold is the parameter pack. And the right or left indicates where are the 3 dots in relation to the operation. So we are talking about a right fold if the 3 dots are at the right from up, and we are talking about the left fold if the 3 dots, the ellipsis, is left from my operation. And for the case of a binary fold, it's slightly different because we now have an additional init. So the form is pack op dot 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 op init, or init op dot 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 op pack. And this helps because we can face an empty pack. And for this situation where we have an empty pack, we can provide this init, this initial value, or however the catch-all value, however you like to call it, which will added or used in this fold expression. It's essential here that all ops, especially in the binary case where we see 2 of them, they have to be of the same type. So you cannot say pack plus dot 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 minus init. It has, for example, then to be pack plus dot 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 plus init. So there's no mixture allowed. And what can I do with that? So at the right, I have this function template print. It's a Fertig function template because it takes a type name t and a type name dot 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 ts. That's the Fertig part. And it once again, as we saw it before, takes a const tref as a first argument and a const ts ref dot dot dot. So the parameter pack is a second argument. Technically second arguments. And it first, in line number 4, simply couts the first argument targ. And then I'm using a lambda here. It's a C++14 lambda. It's a generic lambda because it takes a const auto ref as its argument. It doesn't capture anything. And I store it in a variable cout space and arg because what it internally does, it calls std_cout, passes space first in, and then the argument. And now I can use this lambda and apply it to my pack. I do this in line number 9 at A here. So I say dot dot dot, comma, cout, space and arg, and pass args to it. This time we do not have to say args dot 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 because we put the dots in front. So we are talking about a unary left fold here. And this helps me to apply the cout and args operation to each element in the pack. And by that, it saves me the recursion we had before, because this is now one long call separated by the comma operator. And for those of you who know the comma operator, it works that way that only the last return value, if there would be any, is preserved. All the others are discarded. So it returns void my lambda, so that doesn't matter here. And if I now look at this print function in C++ inside, and let it do the transformation, then we can see that I here have the instantiation for my Fertig template. We can see the arguments it's instantiated with. It's with a char array of size 6, char array of size 4, and then an int. Here, hello is my char array of size 6, C++ my char array of size 4, and my int is the 20. So hello is C++ 20. Hello. So then we can see another thing. I'm not like to talk very much about this today. It's how lambdas are modeled internally in the compilers, or they're a class. That's what C++ inside shows me here. So I have my lambda here we are currently looking at. Because it's a generic lambda, generic lambdas are essentially come with a method template as call operator. So I have the different instantiations for this for these various arguments I'm calling this lambda with. So first with a const char ref of size 4, then only with an int ref. And now if we are looking down here, we can see these are the 2 arguments in my pack which are applied as a fold expression to my lambda. So cout and arg is called with the first argument and then with the second argument. First argument as it's in the pack is C++, second argument is 20. So here the comma operator helps us to sequence a couple of calls and apply it together with a fold expression to a function such that we can do the operation there, saving us the recursion. You can see there is no longer the need for a context pair for things like that. In question always is how many arguments can you pass there that it makes sense or that it's still sensible, and that of course depends on your compiler, on your optimizer. There's probably a certain threshold where it may be better to do that in a loop at runtime than having such a long call, but optimizers and compilers are great, so look at a number and maybe for your compiler it's sufficient enough for you. So let's look at questions. What I have here. I have a very specific one saying that on slide 3, why do you use template specialization for the overloads on line 2 to 4? What are the pros and cons of overloads versus template specializations? So roughly, because I would have to type more to create template specializations here. And secondly, free functions trump template functions. So I have to make sure, and I could add with a specialization, that if normalize in line 6, 7, if B is called with a std string, that the specialization is really the function that the compiler calls. A specialization would do that job, but I would have to write more. And if there is a specialization, for example, of std string and the function as provided in line number 2, then line number 2 wins. So I'm on the safe side doing it that way, and I have to write and type a little more and read. So that's why I prefer that solution. I hope that helps. How to decide whether it is appropriate to use templates versus some other mechanisms, performance, code, reusability. Yeah, well, that's probably a question of its own. Simple, short answer is it's hard. You have to know your target, you have to know your use case, and you have to know your benefits and the downsides. So templates can increase your binary, but they probably only do it for a good reason because they're type safe, so they're creating the different versions for the different types you're calling. Without them, you may have implicit conversions and come out with only 2 functions instead of, say, 4 the template created for you. So that could be a thing, but then you're more safe and you can wait whether you want that or not. Reusability is a great thing. So templates make it easy to reuse your code. But in general, you have to look into it more specifically. Feel free to approach me at a conference. We can have a chat about this. This is a longer discussion usually when it makes sense and when it stops. So here's another example for fold expressions. What can you do with them? So before we had this print function, that's nice. Here I have something different. I reused the normalize function we've seen before in A, in the first slide. And now I have a new Fertig function template in B, build CVS line. And its purpose is to create a comma-separated line out of all the parameters I'm passing in. And that means that it has to convert every parameter into a std string and separate each of these strings by comma. Before, with the print, we separated it with a space. So we combine these 2 techniques now. We have the normalize functions, which convert probably everything into a std string. If you figure out that you have a type that isn't convertible to a std string, you have to write your own conversion function of normalize. But suppose we have that, then the pattern here is the same. I'm creating in line number 10 the return variable red. I call normalize here on the first argument. I expect that normalize returns a std string. So I use auto here to deduce the return type or the type of the variable red. And then I once again have this lambda in place This time it's called add colon and normalize. It's once again a generic lambda taking a const autoref for arg, and instead of writing it to cout, it now captures by reference the ret variable and appends the comma to it and adds the normalized version of arg. And arg is the thing I'm passing into this lambda. And then in line number 16, I do the same thing as before in my print function. I use my parameter pack. I expand it with a unary left fold. At this time, I call add colon and normalize on my parameter pack on args. As before, remember, the 3 dots are already in front, so I do not have and are not allowed to repeat them here in the add colon and normalize call. And with that, I have a small little function which helps me to create a CVS line out of arbitrary types, as long as I have the functions to convert them to a std string. So that's a really great tool because developers, users now only have to remember this one function. And if you hit a situation where you have a type that isn't convertible now to a std string, you can come up and write your own normalize function, which does the job. And nobody has to know. Everybody still simply calls build CVS line. That's one application area for all what we've seen so far, for fold expressions, for varied templates, for function templates itself. We then can call it, as shown here below, with a Q string, as I had that before. We can now say build CVS line hello, comma, std string C++, comma 20, and the Q string says at CppCon. And then it shows printf to print it out. So that's how that thing is used or is called. And as I said in the first part, if you call this or if you see only the call side, you do not notice that we are talking about a template. That's cool. What other things can we do with variadic templates? Well, we can use it to compare data structures. The case I'm having here is I have a MAC address. The MAC address is a struct here which has an array in it of type unsigned char, and it has 6 values. Because the MAC address, if you know that, comes with 6 digits. They are often displayed as hexadecimal representation if we're printing them or viewing them. And the idea here is then that I'm creating 3 different variables of my MAC address, MAC A, MAC B, MAC C. I fill them with the values, and as you can see, MAC A and C are the same, just they have different names, but the contents are the same. And only B differs in the last digit because there it has 4 instead of 2. And the goal is that I'm able to either, or in both versions to be precise, to call a function or something called compare, which is able to compare my MAC address or the array in it to a value against the value. As shown here on line number 13 and 14, that should tell me whether each element in that array correspond or equal that number I'm passing in here or not. So for my MAC A, that should yield to true as the static assert indicates, and for my MAC B in line 14, that should return false, my compare, so I have to negate the result here to make that static assert pass. That's the one application. The other one is that I would also like to be able to compare 2 MAC addresses with each other, as shown in line number 17 and 18. And the key idea is I do not like to have to remember different function names. So I don't want to have something like compare array and compare value. I like to call it compare because they're doing the same thing, just once against a value and once against another version of a MAC address. Solutions I've seen in the wild so far is using macro function, which then has the 6 cases already expanded because we know that we are dealing with a MAC address, so we can unfold that and use that function macro to make it easier to read in the code. Another version is that function macro, or even a function we have which takes the array and then loops in a for loop over it. It knows that it's of size 6. And if you lie about this or you unintentionally passing in a shorter or larger buffer, then you are screwed. So we also like to be that thing type safe. And we can do that. We have seen enough about templates so far that we can do that. And we, in fact, can do that in 27 lines of code. Okay? If you not like to refer to something like a std algorithm, if you like to unfold it and do it, if possible, at compile time, this here is a solution. We are starting this time from the bottom to the top, because then it's more readable. So at the bottommost, at B, I have a function called compare. It's a function template that takes a type name t and my size t parameter as before. I'm using here the technique to let the compiler deduce the type and the size of this array. So compare in line 24 essentially takes two array references of size n. So the two parameters a and b both take a reference to an array of size n. Key here is that a and b have to be of the same type, both have to be of type t, and they have to be of the same size. Both have to be of size n. Okay, if you pass in differently sized arrays, this will result in a compile error at compile time, of course. You can allow this, but what will that mean? It's always false because there are elements you cannot compare, something like this. So let it fail fast, let it fail early, let it fail at compile time. This is what this does. And then internally compare refers to another function in the namespace details array compare, which is also called compare. It passes in a and b, so in two arrays, and then as the third argument that function takes, it calls the function from standard library called std make index sequence. And you can see by the encode brackets there, it's once again a template and it takes the number n. So it takes the size of this array. And what std make index sequence does is it creates a sequence from 0 to n minus 1 of numbers for us. And if we are looking at the details array compare namespace in line number 14 and 16, we see we are dealing with another function template called compare. It takes a type name t as the outer one and the size n as the outer one as argument. And then we're first looking at a non-type template parameter, which is a variable pack. My size t ... I. Okay. And now compare itself takes once again two arrays, which the compiler deduces the size and the type for us, and as a third argument, something of std index sequence of I ... So that thing gets expanded because we are looking once more about a template. And the cool thing here is now I can refer to my parameter packs elements I. In line number 19, I can now say I like to compare A at position I with B at position I for equality. And I apply the Boolean AND to this operation, and then I expand it. So here we are looking at a right fold. By that, essentially, my array gets unfolded and each element of A and B get compared with each other. We'll look at this in C++ Insights in a moment. And the same thing is done for the single array compare as we have it in A. The only difference is that now I'm passing in only one array and the value, but other than that, it stays the same. And if you look at this in C++ Insights, you have that here, then we can see that in fact the compiler creates what I've told you for us. So if you are looking at this function, which is the function comparing my array to a value, then you can see it's instantiated with type char, size 6. My array is of type unsigned char and size 6, and then with an int. And that's interesting because when I wrote this code initially, I used, instead of u here, I used t to have my value. I'm comparing it to the same type as my arrays type. But it turned out that due to the implicit conversions, which are not happening in templates, it didn't compile in a lot of cases, and there was a lot of typing that we are now talking about an unsigned jar or an unsigned short, something like this. So in this case, it felt easier to have a different value, a type available or possible to be passed in, which in this case is int. And then we are seeing the magic of the std make index sequence. This is the index sequence from 0 to 5, so from 0 to n-1. And then here we can see a at index 0 equals b, and a at index 1 equals bb, and so forth. Equals b, sorry. And all the time we can see that a is promoted to an integer with a static cast. It's another thing C++ Insights shows you. And the same thing happens, of course, for my other compare version, where we are comparing the two arrays with each other. So it's the same thing that you can write by hand, but this time the compiler does it for us, which is always great if you don't have to type it ourselves. This is the code, the 27 lines it takes in C++ 17 to come up with that. In C++ 20, we can reduce this to 13 lines of code. It more or less does the same, but in C++ 20, we have the ability to have lambdas with a template head. As you can see, for example, in line 4 and 11, it starts with return and then the brackets for the captures of our lambda, followed by the angle brackets, which we know from templates. And in that, we can specify the template parameters. So this is the only case where you're technically looking at a template or writing template parameters, but you don't write template in front of it. And now my lambda takes a parameter pack, non-type parameter pack, as before my Fertig function in the namespace, and it does essentially the same job, but I don't have to have all these additional functions in namespaces lingering around. So this is a more compact version to write it. It's the power of C++ 20. Then we are having one more thing. These are variable templates. Variables can become templates in C++ 14 as well. This helps us to define constants like pi and have it converted into different types. So if you define it for double, then you have the 3.1, 4, and so forth, whatever your precision is there. And if you convert it to an int, you only have the 3. But we can also make template metaprogramming, TMP code, more readable. If you think it's readable at all. If not, with that, hopefully it gets readable for you. So the example on the right is something we had only even seen in the first part, already seen in the first part. It's where I'm creating my std integral constant. I have the false and true type, and I have the primary template is pointer, which always yields to false in C, and then I have the specialization in D, which yields to true if we are passing in a pointer. And the thing here is, if you look at line 25 and 26, this is why TMP code often gets so ugly to read or to write, because I have to write is pointer in angle brackets, my type, : value. This : value is all over the place. It hinders readability. So variable templates can help us in a way that now in line 21, I'm defining such a variable template. It starts once again with template and then in angle brackets type name t, so it takes a type parameter. This thing is of is const expr, the variable is of type auto, and I name it is pointer v. This is the convention to end it with v if it points to a value. And then I say equals is pointer in angle brackets t : value. By that, essentially, this is pointer gets to be a Boolean, which points to the value or stores the value of this instantiation. Because all this happens at compile time, this yields to is pointer v either being true or false for your specific type. So technically, you can have multiple is pointer v variables in your code because they're all instantiated for different types. And all that helps me to write line 26 and 27 shorter than before, because now I can say is pointer v of int star or not is pointer v of type int. So this is the case where a variable template helps you to make your code, your template code, look a little bit nicer, and it also helps you later on if you like to refactor and rename value, for example. There's another technique we haven't talked about yet. That's SFINE, which is short for substitution failure is not an error. And this is needed and it's helpful because whenever the compiler looks into instantiating a template and it turns out that this instantiation would fail, the compiler silently discards that and it tries another version or another function. If that all ends for the compiler in having found no function to instantiate, no function template to instantiate with that given set of variables or types, values, and there is no free function, no global function available with the same name that takes these arguments, then that results in a compile error. But if the compiler finds another template, same name but different argument combination that matches, then all the previous versions which failed, you never know about them, but the compiler instantiates the version that works and we're all happy. If it's not working, then you're probably getting out this page-wise error output we briefly talked about. And where does this help? And why do we need these? Look at the example I've shared with you in the first part. I have this equal function that compares whether a and b is equal in line 4, and then I have a specialization for type double. Because, as I explained there, floating point numbers have to be treated a little bit different than non-floating point things. Yet, that thing works, but we have more than one floating point type in C++. I mean, in C++, of course, we have different ways to do things. So we have not only double, we have also float. But this isn't caught here. So what would be the solution? Duplicating my template code from line 7 to line 11 and change double to float? No. Doesn't seem or sound like the right thing. So what you can do is we can use SFINE. And now we are looking deeper into that stuff that usually scares people a little bit away because it starts getting unreadable. SFINE is active here, and I'm using it, I make use of it with std enable if t, as you can see in line 2 and line 9. And std enable if takes two arguments. It takes a condition which is either true or false, and the return type, or a type that std enable if t yields to. And in the first case, I say, okay, enable that thing if t is not of type floating point. And then the result of my enable if should be of type bool. So that's like before. And then I have the second version in line number 9, which says enable this one if t is of std floating point. And of course, keep the same type, keep it bool. If you look closely at this, I put this enable if on the return type because there's no other return type. Essentially, that enable ifs makes up whether this function has a return type or not. And if there is no return type, the compiler cannot do anything with that function, so it throws it away. That's this FINE here. So that means that I now can call this with a double, with a float, with an int. And if I call it with a float or with a double, the function in line 12 will be chosen, and otherwise the one in line 5. So I see another question here. Any reason you're using template class T instead of template type name T? Here it seems to be the first time. Yes, I switched because simply it works. So you can use either type name or class here. And this is just another way to confuse people new to templates. There are a few places, I'm not have the time to talk about this today, where you can only use type name or only use class. But in the template head, you, for the most cases, can use either type name or class. They are changeable. For me personally, I usually use type name because class refers for me to an object, but I can also pass built-in types like int, like char to that thing. So I grew up a little bit using type name for that instead of class, because with class I'm declaring new types. But that's just my my rule of thumb. Oh, and I have a question here. I will answer you later. Do you have a slide like this I'm showing here with concepts? I guess yes. So let's pause there. We have this Swinny. Oh, okay, wait. The only reason Swinny works is because the equal returns. Swinny is here put on the return type. You can also put it either as an optional template argument into the template head or as an additional optional parameter into your equal function signature. Both versions are visible to users, so they are often confused, asking what they have to pass as the second or third argument here. So my rule is put the Swinny condition, if possible, as the return type. And only if that doesn't work, put it somewhere else. So this is why I'm showing you here. And yes, this is why this this whole thing works, because a function without the return type is not a function. So this is where the compiler decides, okay, I have to throw this thing away and try another version. And this is either the version where it's a float or where it's no float. So aside from Swinny, we can use something else. We can use a technique called tag dispatch. Here I have that. Still, we are talking about this equal function, a little bit different now. I have from the bottom to the top in line 19, I have my function template equal. It takes the two parameters a and b by constref. And then inside I'm using a const expr if, and once again querying the type of t at compile time, checking whether it's floating point or not. If so, I call another equal function in my internal namespace, and I'm passing a tag type floating point to it. You can see that I'm creating here inline an instance of floating point with the curly braces. And at the very top there, you can see I have these two structs, not floating point and floating point. And in the internal namespace, I also have two equal implementations, one for the general case where I use the equal operator and one for the case for floating point types. And the floating point type takes a third argument of type floating point. The first one takes one called not floating point. So by passing in line 24 and 27, or forwarding my arguments a and b and passing then either floating point or not floating point as an object, the compiler can select the two templates above. And the good thing is the compiler is so smart that it figures out that this is an unused parameter which doesn't do anything. It's only used to select the appropriate overload and to instantiate the template. So you will not even pay for it. It's just like having a switch to switch between the two functions. This is a version with tag dispatch. And if we recall what we seen earlier, there was this build CVS line function, the function template. And this was good, this was nice, but there's one thing to it some of you may have had an issue with so far, and that's it works only with normal strings. So not with white string, or more precise, an UTF string, things like that. So let's add that functionality. be aware the next slide will be full of code, but you're here for that, right? You know most of it because you've already seen it. So here it is. We are starting adding tag dispatch to that thing. So in line number 1, line number 2, I'm creating 2 tags, local V, local S, and local WS. They stand for, I have either my local with a normal string or with a wide string. And then I have a replication of the normalize functions we've seen before. They're more now because I have one for the regular strings and one for the UTF-8 or wide strings. And they're doing their normalize thing there, so returning the correct string. So either a std W string or a std string. We once again have all the combinations. And the specialty compared to the former version is that my normalize functions now also take a second parameter, and that's my local. It's either local S or local WS. This is, as in the example with the tag dispatch before, to help the compiler to select the correct overload. And then, of course, I have my catch-all normalize function templates here in line number 9 and line number 16, doing the appropriate things, either if it's a regular local S or if it's a local WS. Once calling toStd string and the other time calling toWstd string. My build line CVS function, as shown at D in line number 18, hasn't changed that much from a user's perspective to the version I shared with you before. For a regular string, we can just call build CVS line. The signature of the template, however, changed a little bit because now it has a first parameter of type class LT is the name, and it's initialized with local S. So template parameters can also have default values. And if a user only calls build CVS line, they invoke the functions with a regular std string, so not a wide string version. Internally in that function, also little has changed. I'm now using this LT, the first type that's passed into the template, and pass it to the normalize functions. That's all I have to do. That's all that changed to the version, just reading a regular string. And then I have down there in F in line 31, I have a build WCVS line, which does the same job as before for a regular string with now a UTF-8 string. And it does so by referring to build CVS line. As you can see, it calls that, but it passes as a first argument local WS. So it provides to our template a first argument, and all the others are still deduced by the compiler. This is how I can say, please choose the local WS instead of the regular local. And now someone asked, and this was a question not made up before, someone from the audience asked, how does this equal thing look with concepts? And this is the version in C++20 you can write. So putting tag dispatching aside, we can now say, we have this requires clause here in line number 2 and line number 10. Sorry for the formatting. Clang format wasn't so savvy with concepts so far. That's because, or that's why it says bool equal at the end. But here in line number 2 and line number 10, I say requires in parentheses, and then I can state my requirement. And this is in this case not std is floating point v for t. So the first version comparing things to equal checks whether t isn't of type floating point. If so, that thing passes. It's like Spinne, but much more powerful, and we are doing the comparison here. And down there in line number 10, we are checking if it's a floating point. This is the requirement. If so, then this version kicks in, and we're doing the specialty for every floating point type. The difference to this Spinne version or the tag dispatch version is that with the requires clause, you're telling the compiler the specific requirement and the type that has to fulfill it. And if that requirement fails, the compiler can give you a quite good error message at this point. This is really helpful. And then we have finally template parameters. And you can see them as nested templates. We need them when we need to pass a template to another template. In my case here is I have this function fun that should take a container. It should take any container, but it should be a container. So it should not be a char array, something like this. It should be something like a stud vector or stud list. And the syntax is the same as before. I start at line number 1 saying template and the angled brackets, and then the specialty for my template parameter starts. In A here, I have to tell the compiler that I'm not talking about a template in a template. And I do that by once again repeating the keyword template in the angled brackets. And now I have to tell the compiler the types this template I'm like to take in this template takes. So for stud container, they are typically taking two type parameters. The first one we are often specifying, like in line number 18 here, we say stud vector of int. The second one often goes unnoticed, and this is stud allocator. So I don't have to name them, I just have to tell the compiler the types. So this is why I'm saying in line number 3, class, comma, class. And then I have to give that a name. In line number 4, I have to say class container. And this is one place where you have to say class. You cannot say template there. And then in B, I start telling the compiler that this template now takes a couple of parameters. In my case, a template parameter in line 6, t, and then in line 8, another type parameter allocator. And this is defaulted to stud allocator of t. And now my function fun takes a container of t, comma allocator by reference, and I can iterate over this as shown here in the range-based for loop. And now I can pass in a stud vector and a stud list of char, and they are still their containers. So this makes sure that this function takes a container. It's still a template, so it takes a stud vector of int, a stud vector of double, and all that stuff, but it has to be of the signature of such a stud container. So it has to take a type t as first argument and a stud allocator as its second argument. That's it so far. So we have covered a lot today. We ran a little over time. There would be so much more to say about templates. Maybe we have another chance next year. All that's up to me to say is I'm Fertig. For all of you who were in the first part, they hopefully get the joke. I wrote a book, tips and tricks with templates. It's writing down my notes, how to handle a couple of things with templates. You can get a discounted version. It's on LeanPub if you like, and hopefully it's out there as a printed version soonish. I hope you enjoyed it. Thanks for tuning in today. See you later at Remo. Thank you and bye-bye. And I am Fertig.